Okay, what is up, guys? Hope you all are doing well. For today, we're just doing the ionic compounds and metals notes, and then you have 5 questions at the end of this PowerPoint that you need to answer. So for our ionic compounds, one of the first things is our ionic compound here is a neutral compound made up of cations and anions. So what that means is if we're looking at our periodic table and we have an ionic compound such as sodium chloride, so NaCl. We know that Na is going to form +1 ions and Cl is going to form -1 ions. That's because sodium ends up losing 1 electron, chlorine gains 1 electron. So what we're going to see is we're going to have 1 sodium to every 1 chlorine. And this is because these charges here, my +1 and my -1, they're going to cancel each other out so that they end up being neutral. So our ionic compounds are always neutral compounds. So if instead, let's see, we had calcium. So since calcium is in group 2, it's going to lose 2 electrons. So it'll have a +2 charge, and chlorine is going to have a -1 charge. So in order for us to cancel these charges out, I need to have 2 chlorine atoms, right? Because that would give me a -2 charge. So my formula would be CaCl2. And that's because the +2 charge from calcium and the -1 charge from chlorine, I need to have 2 of these -1 charges to cancel out my +2 charge from calcium. Okay, so what this is here, this is our chemical formula for calcium chloride. So that's calcium and chlorine in an ionic compound. That anion, we always add "ide" to the end of it. So it's calcium chloride, and this is the chemical formula, which just shows the number of atoms of each element in that kind of representative particle. So we can call this the chemical formula. We can also call it the formula unit, because the formula unit for an ionic compound is just the smallest whole number ratio of cations to anions. And so one thing that we need to know is that in our ionic compound, it's not like we have little particles. What we have is just an assortment of negative and positive ions. So here our example is sodium chloride, and we have this assortment of sodium chloride all throughout, but we know that for every 1 sodium atom or 1 sodium ion, we have 1 chlorine ion because of the formula unit, or our chemical formula, NaCl. There's only 1 Na and there's 1 Cl. If it were calcium chloride, CaCl, it would be for every 1 calcium, there are 2 chlorine atoms because CaCl2. So that 2 here represents the number of chlorine atoms in our ionic compound. So moving on here, this one's pretty self-explanatory. Properties of ionic compounds, you guys can read through that. The reason why they have these properties is because of the very strong attractions between ions. It makes it so that you need a lot of energy to pull those ions apart. And then also, our ionic compounds, when they are melted or dissolved in water, they're going to conduct electricity because they're going to kind of break up into their different ions. So we'll have positive ions and negative ions. In this case, we've got positive sodium ions and negative chlorine ions. And what happens is when we put a voltage in here, we've got a negative side and a positive side. My positive ions are going to be attracted to the negative side, so they're all going to flow towards the negative side. My negative ions are all going to flow towards the positive side. And so that flowing of ions actually creates this electric current, or allows this electric current to flow. And that's why it's able to conduct electricity. One thing that you need to just know is that ionic compounds conduct electric current or electricity when melted or dissolved in water. Okay, so moving on to metals and metallic bonds. Biggest thing to note here is the structure of metals are sea of electrons. So basically we have our metals, and then their valence electrons are free to just kind of like flow throughout that metallic substance or that metal. And so they're held together. These different atoms of metals are held together because their positively charged nuclei are attracted to those free-flowing electrons. And so you kind of just have this like sea of these free-flowing electrons here. And since they're able to flow and they're not held in place, they're free to move, we end up seeing the characteristic properties of metals: malleability, ductility, and the fact that it's a conductor of electricity. So I'll explain this more on this next slide here. So one of the things I like this image, because it really kind of represents this well, is malleability is our ability to kind of hammer a metal into these sheets. And so the reason why this metal doesn't break or crack is because of the sea of electrons. So when I hit this metal, even though these positive nuclei are coming close to each other, since those negative electrons are able to flow, they almost like buffer. They almost act as a buffer between these positively charged nuclei. And so it allows them to kind of flow, and they fill in that space so that these positive nuclei don't repel each other and cause that cracking or that brittle behavior that we see with our ionic compounds. So with our ionic compounds, if you read this information here, it is explaining what's happening here in this image. So if I hit an ionic compound, what's going to happen is you see that my negative charge is lined up with my positive charge, and they're attracted to each other, and it's holding them in place. But when I apply enough force to it, it's going to shift that negative down close to the other negative, and because they are repelled by each other, it's going to force this piece off of the other piece. And so that's where we get that cracking and that brittle nature of our ionic compounds. Again, going back to our metal, because we have these free-flowing electrons, those electrons get in between here, and they're able to kind of buffer that and cause it so that there is no repulsion between our positively charged nuclei. Our alloys, pretty self-explanatory. Basically, we have a metal, and then we add in different elements into that metal. And the reason why alloys are important is because they oftentimes have more desirable traits or more superior properties than just that element or just that metal alone. So those other elements help to like strengthen or increase the desirable properties that we want in that metal. And then our two types of alloys, substitutional and interstitial, again, pretty self-explanatory if you just read through this. Basically just substituting an atom of a metal. So the blue is that original metal. Since they're about the same size, we can take the other element or the atom of the other element and just like place it in the place of one of those metal atoms in each of these different places. Whereas interstitial, the green is our metal atoms, and then the purple is that other element. So it just fits nicely in between our metallic elements or our metallic atoms. And then this is your assignment here, so go through. You can use this video to help you, use your notes to help you on this assignment. It shouldn't be too bad. For number 2, just remember carbon, oxygen, and hydrogen. If these are bonded together, what kind of bonds are they forming? If they don't form ionic bonds, then it's not an ionic compound. So that's the one thing that I would say to help you on that one. And with these, again, look at the group that they're in and the charges that they're going to have. And you're going to have to balance those charges out because our ionic compounds, these are both ionic compounds. They need to have a overall neutral charge. So you can complete this either on Notability, or if you want to do it on a piece of paper, take a picture and just submit it along with, submit it with this assignment on Google Classroom.